Hello students, today we are going to deal with the new wave properties of the light that is called diffraction. In the diffraction we will be considering the diffraction from a single slit, from the double slit and the width of the central maxima that we are going to observe. Hello students, so now we will study a different property of the waves called diffraction. Now we will see how diffraction produces the physical patterns that are observable in case of light. Now, what is diffraction? Diffraction is the phenomenon of bending of light around the corners and the encroachment of light within the geometrical shadow of the opaque obstacles. It is called diffraction. Now, you may have observed this. Now, what exactly this wants to tell is this. Is that suppose this is a cardboard. Okay. Now there is a screen here. Suppose there is a light beam that is coming here like this. Okay. This is the screen. Now what do you expect to observe? What we observe is that the light should appear like this. Right? Light above this or below this can't cross this whatever's cardboard or whatever is being kept in which the slit is there. Now this region should be the bright region due to this light, not these regions. These regions are the geometrical shadow regions. What are these regions after this? These are the geometrical shadow region. Okay. These are the geometrically shadow because the light travels in a straight line and based on geometry this is a straight line, this should be the shadow region, no light should be there. But what we practically observe is that there is some light present in this region. There is some light that is present in the geometrically. You will have light here, you will have light here, you will have light here, you will have light here. So how does it happen? Like light travels in a straight line. How does it happen that it goes like this? So it's not because that the light is. It's not because the light rectilinear propagation of light is wrong. Obviously, light propagates rectilinearly. It's the wave nature that is being manifested here. What happens in wave nature? That all this. Now this point, this will act as a source of wavelet. So it will emit waves like this. So because of these waves, and suppose we consider these waves. Now all these waves, this will have an interference here also. Okay, and you will have brightness and darkness here also. This is the diffraction pattern. It's a bending. It's called the bending of light because you are expecting light to go like this and actually you observe light here. That means the light has bent. So that's what diffraction is, and this is happening due to that theory of waves coming out, they are interfering. Now the wave, since it is coming here, it will expand up to this region, right? You can see this wavelet, it's coming in this region also, below this region. So this is responsible for the diffraction. Now see what will happen when we have an angle of diffraction is 0. Now angle of diffraction is 0 means central one, it passes like this. Now what will happen, suppose all of this light is coming from here to here. Now the light crosses this. If you have a converging lens, it will converge all of this to here. Okay. Now when do you expect to see a maxima here? When will there be a maxima? There will be a maxima when all of these points, whatever light rays, this light ray, this light ray and this light ray, only when they will have a path difference of integral multiple of lambda is that you will have a maxima, right? Because for a maxima you need that the path difference should be either in terms of wavelength it should be lambda, 2 lambda or 3 lambda, and in terms of phase difference it should be 0, 2 pi, 4 pi, something like in that multiple. So there will be a maxima only when this path difference satisfies the condition. Now what you can see is that obviously this path differences are not equal. It appears from here the path differences are not equal, right? But how do you get a maxima here? It is possible by two reasons. One is that the extra path that it has traveled is actually a multiple of lambda. So if I traveled actually a multiple of lambda, that means again it's the same wave, because for the wave cannot discriminate now. Once you have traveled an extra lambda, you are again in the same state. Same thing can happen. Another thing is very observable. If you can observe this, and although it's not being very frequently mentioned in the books, what is there the optical path? If you see that, what is the optical path that this ray goes? This thickness is only x. This distance is only this small x. So what is the optical path? It is mu x. Now if you see what is the optical path that this goes, this is mu times y, and y is much larger than x, right? Mu is always greater than 1. So that means, although it appears that this length is larger, which is in the air this has only gone this distance, but because of this length which was actually y, the effectively in terms of the wavelength, in terms of phase, it has gone mu into y. So it has actually gone larger distance. Means in the air obviously this distance is small, but the optical path is larger for this because it has gone larger length in the lens. So actually this has the same phase when it reaches here. Okay. Now what will happen in the diffraction of light at a single slit? Means this is a slit. If you see, this is a single slit. Now this slit, we assume that this slit is divided in two halves like this. Now let us analyze the situation. We have considered it to be divided in two halves. Okay. Now we considered it at we try to consider at a point P1. Now what will happen? If you see the light coming from this point, it goes this length, and light coming from this point goes this length. Now if the path difference between the two is lambda, it will be a bright. If the path difference is lambda by 2, it will be dark. Now how to find out the conditions for the maxima and minima? Now since this is like an infinite number of point sources, we consider for our convenience only a finite number here, but actually it's an infinite number. Okay. So now if the path difference between this and this, path difference between this and this is lambda, then only it will be a maxima, otherwise it will be minima. Now if you see, now since this is being observed at an angle theta like this, theta 1. Okay. So now what is this distance? This distance is d by 2. If this whole distance is d. Now what is this distance? If this distance is d by 2, okay, and this angle is theta, that means this angle is also theta. So what is this distance? This distance is d by 2 sine theta. So now if this distance, this is the extra distance, sorry, this up to this is the extra distance that this ray goes. Now if this extra distance is equal to lambda by 2, you will have a dark fringe, you will have a minima. That means d sine theta equal to lambda. Now although you can see that I have considered this point 0 and this exactly at the central point, right? This is the idea. Now since you have a point from here and here that are interfering in this manner and giving you minima, for every other point, next point that you consider here, there is a corresponding point here that will also interfere destructively, because again the same condition hold true. Again the path difference is this, it is lambda by 2, it is giving dark. Again you move to point 2, so point 2 and point 7, they will again give you the same, so again there is a minima. So in this manner you finally get a minima here. This is how the diffraction is happening. Now here the wavelets of the single, what I have written, the pairs 0, 6, 1, 7, 2, 8, these all they interfere destructively with path difference lambda by 2 and gives the first secondary minimum. So that's what I was telling here, is that this 0 will interfere with 5 to give you minima when this condition satisfied, because when the path difference is lambda by 2, what is the path difference? Path difference was only this length. part difference was, if you see here, let me remove this. Part difference was this length, right? Part difference was only this length. Now if this length is lambda by 2, this was the extra path that this is going, right? So if this extra length is equal to lambda by 2 means it has gone ahead by lambda by 2. Lambda by 2 ahead means it is out of phase, it's totally out of phase. So it will be minima. And now what is this distance in terms of this length? If this is d by 2, in terms of this length, this is d by 2 sine theta, because this is theta means this is theta. So this is d by 2, this is theta, this is 90. So what is this distance? This is d by 2 sine theta equal to lambda by 2. This is for minima. So correspondingly for point 1 you will have 0.6, for point 2 you have 0.7, for point 3 you have 0.8. All of them they are giving minima, and you get a total minima due to all of this interference of all of these points, they give you minima. So what is the condition for minima? It is d sine theta equal to lambda by 2 means here it is lambda. Had it been 3 lambda by 2, 5 lambda by 2 or anything, it would have been the same situation. So you can write it as 2n plus 1 because it's odd, it's an odd integer, so it is 2n plus 1 lambda. Okay, had this part difference been this, it would have been. So at an angle of diffraction theta equal to theta 2, consider a different position like this, at a different angle theta. Here we can divide it into 4 parts, and again we apply the same logic that for this portion and this portion you will have this interfering with this point interfering with this point interfering with this destructively and giving you a diffraction minima. Similarly in this portion it will interfere with this portion will interfere with this, and it will give you a diffraction minima. Okay. And the same idea here, the pair 0, 3, 1, 4, if you see here 0 and 3, 1 and 4, 5 and 3, they are all giving you 5 and 2, 3 and 6. They interfere destructively with part difference lambda by 2. These are interfering with part difference lambda by 2, giving a minima. So this is what I have shown. I have put here for different angles of theta, what is the kind of diffraction pattern that's visible. So what is happening? What is this height? This is the maximum, means here the light intensity is maximum. Why? Because here everything was interfering constructively. If you remember, the light was coming like this and like this. So there was a maximum here. Then there is a minima happens here. That means at this point b sine theta equal to n lambda is being satisfied. Then similarly when you reach here, again you have a maxima, again minima. This is how this pattern is varying. This is diffraction. Okay. Now how to find out the width of central maxima? Means this is central maxima. If you go back, what is the width? When I say the width of central maxima, what do I mean is this. This is the width. This from here to here. This is the width. This is the width of central maxima. Central maxima, its value here it is 0, here it is 0, and it goes to maximum here, and it is. So this length is the width. So we will try to find out what is the width of the central maxima. So in this phase, we do the calculation here. Now we have seen that tan theta is y1, this theta 1. Now we know that when theta is small, we should always keep in mind this, that for a small theta, this is very frequently used, sin theta is equal to tan theta is equal to theta. Now here theta is in radian, it's not in degrees, so you have to keep this in mind. Okay. So here theta 1 is this. So what is tan theta 1? This is y1 by d, right? This length is y1, this length is d. So tan theta is p by d, perpendicular by base, you get y1 by d. So, or theta 1, since theta 1 is very small, you can write it like this, right? D sin theta 1 is lambda. We saw this is the condition for minima. That means theta 1 lambda by d, you can write it like this. So y1 is lambda d by d. Okay, this is y1. That means what is y1? y1 is this length. So suppose this is happening, this is central, so that means this length is happening at what? Lambda d by d. This is y is measured from the origin, so this is y, lambda d by d. So what will be the width? Width will be twice of this, because it expands to the other side also. So this central maxima, it's 2 lambda capital D by small d. This is the width. This is the width of central maxima that we got here. Okay, let's solve a question now. A screen is placed 50 cm from a single slit which is illuminated with 6000 angstrom light. So lambda you have, or you can write it like this, minus 10 angstrom, sorry, meter. Now it is placed 50 cm from a single slit. That means what is capital D? 50 into 10 to the power minus 2 meter. Okay. Diffraction pattern is 3 mm. What is the width of the slit? What is this diffraction pattern is 3 mm? This is the width of central maxima. This is the width of central maxima, that is 2 lambda capital D by small d. This is given to you is 3 mm. So we write in terms of meter. What is the width of the slit? What is the width of the slit? The small d. So what we do? Simply put the values. Small d is okay. So put the values. 2 into lambda is given to use this 10 to the power minus 10. What is capital D? Capital D is 50 into 10 to the power minus 2. Divided by, you had this given 3 mm. Okay. So if you see what are the values, this will add up with this, give you 10 to the power minus 12, minus 3 goes up, this becomes minus 9, and again you have 3 zeros and 1 zeros, these are 4 zeros, this will make this minus 5. Now this 3 will make this 2, so this is 2 into 2 into 5, 20 into 10 to the power minus 5, so this is actually 2 into 10 to the power minus 4 meter. So if we write it this in terms of mm, we can write it small t is actually equal to 0.2 mm. So this will be the slit width. Slit width is this length. This is slit width. Sorry, this is not here in this case. So we have this. This is diffraction. This was the slit width, small d. The screen was kept capital D from here, and then you observed a maxima here like this. And then there are minimas that we have seen. This is how this is going. This is minima. This is how it is going. Now this length was beta. This is small d, and we have to find out this. So I hope you have understood what the diffraction is and how this behavior can be explained using the same interference phenomena. Now what I need to mention here is that interference and diffraction are essentially the same phenomena. If you have seen what is happening exactly is the same interference pattern. It's just that the number of sources are actually infinite. So a very great scientist, Feynman, he said that actually there is no difference between interference and diffraction. It's when the number of sources are very high, we call it diffraction, and when the number of sources are finite, we call it interference. Like in the double slit experiment. Now when you had two sources, you know that there are two sources, we call this interference. Now here there was a slit width where we had to treat it like large number of sources because this slit width was very large. Here this is very small, although I have exaggerated, it's like very small slit widths. So here this is like interference. Now but when you are considering one particular width and where you have a large number of point sources, so it's like an infinite number, very high. So here you call it diffraction. So essentially there is no difference, but when the number of sources are high, you find it diffraction, and the pattern that is visible is again different. That's important. The diffraction pattern is like this. The interference pattern, where if you remember what was the interference pattern, it's always the same value, minima again the same value, again the same value. Pattern is like this. This is the interference pattern, and the diffraction patterns are like this. Means if you draw it here like this, diffraction patterns are diminishing in height. It's diminishing in height. So this is diffraction and this is interference. This is essentially the difference between these. This we have solved some question, we have dealt with it. So I hope there is no problem understanding it. So we have done the diffraction part of the light, and we have seen how the wave properties in terms of diffraction manifest itself. In the next part we are going to deal with the polarization of the waves. So for more on this, stay tuned to Ask IITians. Thank you.